Hello everybody and welcome to the webinar. Thank you for taking the time to join us today. We're going to give a case study today on a tunnel construction monitoring project, taking a look at when things move, some of the instruments that we used and some of the data that we saw during these events. The presenters today will be myself, Steve Billingham, and Dr. Melih Demirkan, my colleague in North America. Melih heads up Rite Geosystems in North America. He's got over 20 years professional experience on a variety of geotechnical, seismic, hydrogeological and geoenvironmental projects. He's also co-authored more than 20 peer-reviewed publications. For my own part, I started my career in the installation of geotechnical instrumentation actually, and did that for about 10 years worldwide. I've then moved through a variety of roles and headed up 3 different companies, always supplying geotechnical or environmental monitoring instrumentation, and at the moment heading up United Kingdom office of Rite Geosystems. So just to give you a little bit of overview here, Rite Geosystems is part of the Encardio-rite Group. We're a global company with, as I say, offices North America, Europe, in the Middle East, Southeast Asia, Australia, and of course head office in India. We've worked with the vast majority of the large construction companies and consultants across the globe, and we've got some considerable expertise. That is backed up, I think, by some of the stats on the left-hand side of the slide there, which show you the amount of kilometres of various tunnel projects that we've put instruments onto, and a number of the other projects that we've been involved with. So just briefly a little bit more on Encardio-rite. We've actually got some deep heritage here and over 54 years of experience in the company. We've got a network that we work with of probably 450 professionals and have supplied products into around 55 countries. The strong part of that, I think, which is worth sharing, is that we have our own research and development department, and we manufacture the vast majority of sensors ourselves. The key there being, of course, is that we can react very quickly to technological changes and indeed to changes in market demand, be they for technology itself or for volume of supply. As you'd expect, we work to stringent quality systems and international standards, which we currently work to ISO 9001:2015. So instruments. Here we'll see just a few of the instruments that are used on the case study project that we're going to talk about. It can be occasionally that with instruments, if one of these sensors gives a reading that wasn't expected, people call into question, is the sensor working? Is that reading correct? Well, we would say with some high confidence that yes, very much. If a sensor gives a reading that wasn't expected or is a little odd in comparison to its trend, investigate it. Why do we say that? Briefly, with these 2 instruments here, to give you an idea of the testing that goes on before any instrument is supplied and put onto a project. With piezometers for water pressure, we supplied thousands of these over the last 30 years. We use a technique of electron beam welding, which hermetically seals the sensors, preventing dust and moisture ingress, and makes them highly resistant to corrosion. The actual tests that are conducted on each sensor before it goes out and is installed on a project, we will run them from -20 to +80 degrees centigrade. We will do a sustained high temperature test, whereby we take an average, derive standard deviations and unique gauge factors for each sensor. We will reverse pressure test them. We will overpressure them to 150%. We test them each for 3 days and ensure that there's no variance that is unacceptable. And I think more significantly as well, we apply a pressure on, pressure off, 2,000 cycles of that pressure on, pressure off to each sensor. So it's been comprehensively tested before it comes out to you as the client. Similarly, with INPLACE inclinometers, which you can see there in the lower image, the sensor with a cable on it, these again have a 15-day test cycle where no variance above 0.015 of a degree is allowed. Each sensor is submerged for 24 hours to 60 meters head water pressure, or 6 kilograms per centimeter squared. In fact, we can test these to 100 meters head pressure, or 10 kilograms per centimetre squared. Thus, each sensor is essentially IP68 rated, and again, no dust or moisture can get into this sensor. All of the sensors, be they vibrating wire technology or MEMS technology, can be wireless or cable connected back to the data logger. They're simple and easy to install, increasingly simple and easy to install, in fact. A couple of other pieces of instrumentation which are used on the project we're about to see. Here we have a digital inclinometer. This is the manual version of an inclinometer, where the probe is lowered down the access tube and readings are taken manually. These systems haven't really changed probably over the last 20 to 25 years, other than, as you can see there, the readout unit is much smaller. And in fact, it's very powerful now with the software that you use on that. It's essentially on your mobile phone, you can run this software, and it allows you to check historical data, be it over days, weeks, or months. And indeed, you can transfer that data to and from site. Whilst on site, with no need to leave and gain access to readings. Data loggers, extremely compact now. You have integral GSM, GPRS modems built in. 60, in fact, in strictness, 61 sensors per channel can be handled by the data logger. So as in the case of the image there, 3-channel data logger can handle 183 sensors. It can also handle a variety of sensors. So on the case study we're about to see, it's quite easy to put in vibrating wire sensors, be they piezometers, strain gauges, and a mix of IPI sensors if installed. Power options, again, depending on where you are in the world, you may wish to use mains, solar and battery, or indeed a mixture of those. So it could be internal batteries backed up by solar. Another option that is possible is automatic robotic total stations. And what we're really saying here is you can see the image of that device there. Where these are particularly useful is where it's hard to access site to get back to the same location to take readings, or if there are a high number of sensors or targets to be monitored, this device is particularly useful. It also allows you to send data wirelessly from that device, and indeed you can connect to it remotely from anywhere, reconfigure it, set it, etc. So increasingly popular piece of equipment when high numbers of sensors or targets need to be monitored remotely or in hard to access places. In fact, we've used something similar on another project, which we're not showing today, but where readings had to be taken every 15 minutes. The data had to be made available to a client within 20 minutes. And indeed, it's been running for some 3 years, and you have about 9 million data points. So 9 million data points takes us quite nicely to talking about data management. I think it's as important to consider data management as it is to consider what type of sensors you're putting onto the project. Quite simply, data management now is hugely versatile and has high amounts of functionality. You can set hierarchy of permissions, so a tier 1 level of people can see the data. If they don't react to it, or if something hits a certain threshold and somebody else needs to see it, you can escalate it. It's completely versatile, and a typical interface here is shown. The background can either be satellite or map, and what you're seeing here is the little icons with numbers inside, the blue and yellow icons with numbers inside, essentially our projects on the map, and you can show all of your projects that you may have wherever you are. Click on an individual project and you start to drill down to the actual sensors that are at that location. Similarly, we can see here there's a small icon of a camera. You can take an image snapshot of each of these locations where the sensors are. That can be particularly useful if you have, for example, 2 sensors on one building wall, one high and one low, and you need a short reminder as to which sensor is which when looking at the data. You can look at real-time data for each of these sensors as well. You just click on one individual sensor, or indeed, as we see here, you can highlight a set of sensors and then create charts for those sensors. Contour plots, perhaps if it's piezometric data, you can plot contours, and indeed you can show animated displacement. Typical graph, what we're seeing here is several sensors over a longer period of time. Again, the versatility allows you to drill into each sensor, click on a certain date, see all of the readings, all of the things you'd expect, whether it's graphical or numerical. The feature I mentioned a moment ago with animation of sensors is just here, and I'm not running this as a live animation, but in short, each sensor, you can see these red arrows coming from some of the sensors, and what the red arrows depict is the direction of movement of the sensor, and the length of the red arrow depicts the amount of movement. So if we were to run that as an animation, you would see these sensors showing arrows creating in these particular directions and certain lengths. As I say, really, data management is important as sensors, hugely versatile and a lot of functionality. Typical instrumentation scheme, the project that we're looking at in just a moment, is deep excavation and tunneling. Instrumentation is obviously determined by designers as to what instrumentation will go on site, and designers have to take into account such things as methods of construction, what is being constructed, the ground, the stratigraphy, budgets, of course, the risks that could be involved, and the consequences if those risks were to occur. So here we see a typical schematic, which is a building above ground, rain gauge, recording how much water may be falling and ingressing into the surface, tilt and crack meters on the building to determine building movement, in-place inclinometer for lateral displacement, piezometer for monitoring water levels, groundwater management while excavation takes place, borehole extensometers, settlement and heave. And here, if we say a diaphragm wall, bolt load cells and tilt meters again for displacement of this wall. As I say, really, the amount of instrumentation used on any project is determined by several factors. On this slide, the instruments we've just seen depicted on the left-hand side here. The part that the clients are really interested in is data, access to data and visibility of data, and indeed, as we said, not to see 9 million data points probably, but to see the exceptions and to see the reports. So within data management, it's possible to create auto reports that are sent out on a weekly basis, which just show the key factors that are required to be seen. In between data being received and the sensors themselves, of course, we have data loggers, those automatic robotic stations, cellular phone networks, wireless nodes, etc. And depending on cabled or wireless, will largely be about topography, line of sight, possibly permissions in certain regions as to what is allowed to be used. So moving on to the case study itself now, we see even in this day and age, there still are, unfortunately, catastrophic events on some projects where slips occur or structures fail. And I'm glad to say that this case study does not cover any of those catastrophic events or have a catastrophic event associated with it. But it is important to monitor and to take note of what happens. So the project itself, here we see, and it's the extension of an existing metro line running from the harbour, shown in the top right of the image, to the main station in the bottom left. And the actual section we're looking at today is depicted by the yellow line, and the yellow line is the tunneled section. Tunnel section is around 2 kilometres or 1.2 miles long, and it consists of 2 underground stations, Station A3 and Station A4, and also 2 annex structures. The annex structures allow for access for maintenance or emergency exit or access into that tunnel section. Above ground, depicted by the red line at each side of the tunnel section, we have elevated structures, and here we have about 10 kilometres in length or 6.2 miles, and there are 5 or 6 stations above ground. Before any construction took place on this project, we were asked to carry out a dilapidation survey, and this consisted of using a drone to fly along the route, taking note of anything within 25 metres of the construction line, and really recording manholes, lampposts, buildings, structures, etc., to get essentially a base set of data, visual data, so that that can then be looked at again at a later stage to see if anything has been affected by construction. A summary of those structural details. From the north cut and cover, it was tunnel boring machine that went through to carry out the excavation for the tunnel, and that moved through to station A3, and then from A3 through to A4 and onto south cut and cover. The monitoring frequency for this project, here's a summary, and you can see that during excavation, pretty much the majority of the instruments were at least monitored daily. Some strain gauges and water level recorders being 30 and 60 minutes, but the vertical inclinometers, which were critical in regard to excavation and depth of excavation, were monitored twice daily. During construction, that frequency reduced, moving more typically to weekly readings, although the automated readings were still done every 30 or 60 minutes. And indeed, there's a caveat that with the inclinometers, there had to be no appreciable movement over 3 consecutive sets of readings, or if that did occur, it would have reverted back to a more frequent monitoring regime. Number of instruments by location through the tunnel section, a fairly healthy amount of instruments, as we said, piezometers and standpipes for groundwater monitoring, vertical inclinometers for excavation. You can see there on A4 that one of the inclinometers was retrofitted with some in-place inclinometers. We've also got surface settlement points and prisms, which we use to cross-correlate again for displacement and 3D movement. So we mentioned previously that one of the factors in terms of determining what is monitored and what is used is the risk on a project. Well, the risk here, we have the stratigraphy for this project. And for the geologists amongst you, there are 3 core formations in this area that the project took place. And they are Gayatri, Barzaman, and Gaxaran. Now, for non-geologists, what those actually are is calcareous sandstones, siltstones, and claystones. And you can see here the colours on the image; those are intertwined between each other. And the critical factor actually for this project is that they were all weak to very weak formations, thus necessitating the need for this degree of monitoring on excavation. Now, just at this point, I will now move over to my colleague Melih, who can take us from this point.
Thank you, Steve. Before I continue, I wanted to give a couple updates regarding to questions. If you have any questions, feel free to send us. We will address those at the end of the presentation. So, as Steve mentioned, there were several sections of the project which we're going to go through and understand the overall structure and the instrumentation layout that was implemented. The first one is the north cut and cover section, where the TBM was launched. So this is the overall layout for this section, and this is the general schema of the instrumentation layout for the most of the project. There were 4 main components were targeted for monitoring. The first one is the movement within the retaining structures, the lateral deflection of the retaining structures, and the second one being the movement of the ground surface, as well as the settlement of the structures, the third-party structures in the zone of influence, and the last one being the groundwater change around these structures in the excavation area. As you can see, a number of vibrating wire piezometer monitoring wells, as well as open standpipe groundwater wells were installed, as well as within the lounge area there were stress tests monitored for the stress, as well as vertical inclinometers for the deflection of the diaphragm wall. So this is a picture from the site. You can see the strain gauges installed on the struts over the TBM, and you can see the groundwater, the extent of ground monitoring outside the diaphragm wall. The second structure that is monitored being these ANNEX structures. There are 2 ANNEX structures. These are underground structures that were built as an emergency and maintenance access to the tunnels during the operation. So these are not stations, but basically vertical shafts to the tunnel access to maintain that access for emergency and maintenance purposes. So this is one of the layouts of the A21 annex structure. As you can see, struts are monitored for stress with multiple vibrating wire strain gauges, as well as the ground surface monitored for 3D with 3D prisms. Similarly, there are inclinometers and piezometers, monitoring wells with vibrating wire piezometers. This is another picture from Annex 1 where the strain gauges are installed, as well as a section, how it merged with the tunnel alignment, as well as the convergence monitoring. And other installation pictures, as you can see, the inclinometer is installed within the diaphragm wall, and some other installation pictures. This is the first underground station called A3. It's a really wide open excavation area. It's supported with diaphragm walls. And this is the overall plan and where the instrumentation has been placed. The number of inclinometers are increased at this section because of the size of the opening, as well as groundwater and surface monitoring was in place. And this is a typical section where the vertical inclinometer has placed, and the overall, excavation scheme with really steep slopes. So as Steve mentioned, the geology here in this area is a little unique in a sense that the rock is weak, but it can support itself with apparent strength. But you have to be very careful with overall design, because there are interbeds and like the overall homogeneity varies from one location to another, which is difficult to predict the engineering parameters. Again, I'd like to show some of our installation pictures. These are the inclinometer casings placed in the secant piles, which comprise the diaphragm wall, and some 3D prisms for 3D monitoring, as well as piezometers that are in place into bentonite peg as a traditional method. This is another annex structure that was instrumented. Again, it's a shaft through the tunnel, and this one is vertical, and convergence has been monitored using prisms and total stations, as well as inclinometers and various piezometers has been used during the excavation. And rest of my talk is going to be on this last underground station, which is a large opening, and significant effort has been put for the integrity and the safety of the overall excavation process. So this is a large station, as you can see, and with various instrumentation in place, and heavily on the inclinometer and piezometer and surface monitoring side, as well as monitoring the stresses on the supporting struts. And one thing actually here I would like to mention is the fact that from this point forward, the majority of my focus is going to be on the east side of this excavation. This is called the head wall, where the TBM breaks through the excavation. And I'm going to talk about the results from these inclinometers, 19, inclinometer 3 and 5 and 2. Again, similar pictures from the site, strain gauges installed over the struts. And an in-place inclinometer picture that is installed after the initial deformations to increase the level of intensity and the monitoring of the deformation. As you know, in-place inclinometers are very handy tools, give you near real-time monitoring of the deflection at the location. Before looking at the results, and I want to give an introduction about the triggering levels that are implemented at the site, which were coded as green, amber, and red, which were all experienced. So basically, the green is almost a design level limit, where everything should be within the design allowance, and red being the serviceability limits, the maximum deformation that the designer thinks that the structure can handle. And amber is usually a percentage of the red serviceability limit. And within the amber zone, usually the contractor, designer, and get together and look at what is going on, since green and amber limits has been exceeded, and they do back analysis and they get some measures to prevent to getting into a red zone. And if a red zone, a red level has been exceeded, usually it brings a stop work order after carefully evaluating the situation and the imminent danger and the risk. And let's look at some results from the site. The overall excavation started beginning and toward the mid of April of 2018, and shortly after, some extensive deformation has been observed at inclinometer 3, exceeding the green levels, which is a surprise at that level. And continuing within April, toward the end of April, as the excavation moves forward, the significant number of inclinometers has shown deformation readings. At that stage, one thing that is important to know is almost no dewatering system is in place, so outside of the excavation area. And one thing also to keep in mind, and because of due to the proximity of the structures around these excavation areas, so the dewatering is a tricky undertaking, because you don't want to really alter the groundwater under the structures around the excavation, but you also wanted to keep your excavation safe. So it's a very delicate balance for the overall performance of the project. And again, sorry about my slides. So again, after observing the initial deformations, and toward the end of April, we have seen again significant deformations exceeding the amber trigger level, so which is an eye opener, and which ended the contractor immediately installing dewatering wells beyond the construction area. At this point, one thing also should keep in mind that the slurry wall in the head wall area hasn't been installed yet while the excavations were ongoing. In the first couple days of May, actually at the very east side of the excavation has reached the red trigger level. And this was due to a couple of hours of kind of malfunctioning and the failure of the dewatering well. And the groundwater levels were rise around 2 meters, which causing the deformation behind the excavation area. So, you know, this was the first eye opener and showed the importance of the overall dewatering performance at the site. Couple days later, and actually this is another view of that event and the May 1st, then another location on the other side of the wall. And couple days after, the watering system again kind of failed and shut down, and the deformations again exceeded the red levels. And this is for, again, a couple of hours, and the groundwater levels rise 1.5 meters, and showing the deformations there. And I hope, you know, thankfully, this doesn't really cause any catastrophic failure, but really tested the limits of the diaphragm wall at the site and showed the importance of the dewatering operations. And similarly, this is from another inclinometer confirming the same type of deformation. Of course, as instrumentation companies, we really always preach about the importance of redundancy at the site. So typically when you are observing such high deformations at the site, you always question the data. And if the data is coming one set of readings, it still may be questionable whether the reading is, you know, reliable or not. So at the site, you know, since there's redundancy on deformation and these inclinometer readings have been confirmed thoroughly with the deflections on the wall, which are measured using automated total station ATS and 3D prism targets. And you can see the deformation scheme on the dates in the, you know, by April 19th and then April 22nd and April, the beginning of May 1st and May 8th, which is the last failure of the dewatering well. So it was really confirmatory of the other readings. So redundancy is the key for overall confidence and for the project and the data. For you know, groundwater levels, one thing as a company we like to use is a fully grounded method, meaning that the piezometers, the vibrating wire piezometers in a multiple fashion, meaning that in single hole we can place multiple piezometers to measure the various levels at various depths, and we fully grout the piezometer. Sometimes this is counterintuitive, meaning that like how come a grouted piezometer would give you reliable reading, and but because of the high sensitive and precision structure of the vibrating wire piezometers, the overall volume change that is required to be captured with the piezometer is really minimal. And due to the ease of the installation, so we really promote and like fully grouted methods. And at this site, we actually have chance to compare the traditional, you know, bentonite packed, monitoring wells, the piezometers, as well as the fully grouted piezometers. As you can see, the data is highly comparable, which give us confidence on the fully grouted method. At this particular application, of course, it depends on the compatibility of the grout versus the overall geology. It's not an off-the-shelf solution. Like, you have to be very careful designing your grout mix. And one thing I want to mention actually at this webinar is the overall importance of the groundwater monitoring and any site. As you can see here, the red lines are showing the groundwater levels, and the green lines are showing the inclinometer readings at the most deflected inclinometer. And there's a distance in between each these sensors, but as you can see, whenever we have an increase in the groundwater, we have an increase in the deflection of the wall. And usually, as you can see, the groundwater is a pre-indicator of the deflection. If we can closely monitor the groundwater levels, and we can really predict the overall outcome and eliminate further deflections at the site. Another result is on the strain gauge data. So the strain gauge data, shows the overall stress and the load on the struts. Since we have multiple data points, but just from one location near inclinometer 3, is that you can also get the increase in the load levels and the strain gauges, those struts, at those deformation events at various dates, late and April, beginning of May, and like 8th of May. All those deformation events has been captured with the strain gauge data. At the end, I think we can get some outcomes from this project in terms of what is important and how should we treat the overall measures and understanding of these deformations. Is that really partial or full failure of the watering system is the main cause of these deformations, or lack of dewatering or failure of the watering system. And there are a couple other reasons that can be carefully evaluated in terms of the cause behind these large deformations, in a sense that the lack of slurry in the head wall and sometimes uneven excavation within the station box, and the quality of the dewatering system and the quality of the diaphragm wall is also really important. So the contractor and the designer have increased real-time monitoring after the initial deformation. We put in-place inclinometers and real-time piezometer readings around the diaphragm wall, and increase the water level measurements, and put additional automated total station 3D prisms for the ground deformation, and increase the intervals of monitoring, as well as additional dewatering wells and some temporary support structures as well. And that's pretty much what we'd like to talk today. And we really appreciate your time. And if you have any questions, we'll be very happy to answer at this stage. You can type those, and my colleagues and myself will try to address those as much as possible.
So I can see there's one question there. Why were more IPIs not used initially? Why were manual inclinometers used? And that's a good question. We typically find that it's often down to budget that people still use manual inclinometers. However, as many will soon calculate, actually, if you're going out, as we saw, with a frequency of twice a day reading inclinometers, then you need a full-time labour team to be going out taking your readings. In addition, some of those locations may be hard to access. So I think typically people are moving across more to in-place inclinometers now. Manual systems are still used, and indeed they are used to take a base set of readings before you put in IPIs. But IPIs are becoming more popular. See, just another one now. See, why is Wi-Fi not used more if it's easy to install? I think that will depend really, as mentioned in the presentation a little bit. It will depend on topography, line of sight. You can work around most structures now in terms of getting signals back from instruments to data loggers and indeed cloud with Wi-Fi, but there's still a place for cabled. It will in some locations also depend on permissions and access to cellular networks. I think I saw some statistic recently where there's an increase in use of wireless equipment, probably about 10% per annum at the moment. That's growing.
Steve, we have another question asking, the IPI sensors work with new nodes gateway system instead of I think Campbell data loggers. So we offer various type of wireless systems for our IPI devices, and it can be through our ESDL30 wireless data logger, which can directly transmit the data through GSM network to the server, as well as we can connect it to radio frequency RF nodes to be connected to a gateway at the site, which will push the data into the dataway server. So we have multiple offerings in terms of like wireless communication of the IPI units.
I can see another question. Could we apply 6-meter interval of IPIs to interpolate data? If I'm understanding that correctly, yes, you can determine whatever spacing you require of IPI sensors in a borehole. So it could be every 6 meters, it could be every 1 meter, it could be one sensor in a borehole. You really determine exactly what you require in terms of the spacing of those sensors.
So another question is how big the risk is for IPI install experience deflection over 50 millimeter. They would be stuck and cannot be retrieved. And at 50 millimeter is an allowable deformation for the casing, and you know, this is controlled mostly with the casing integrity. But for this application, they were retrieved. So, but for larger deformations, yes, there is a chance that you know, if the casings is you know, snapped and broken, and there's a chance that the IPI may not be retrieved.
Somebody's asking, what's the likelihood of errors in monitoring data? What typically causes that, and how do you normally resolve? In terms of errors in monitoring data, as described in the presentation, those are fairly rare now, I would say. If it is believed that there is an error, depending on what instrument it is and how it is installed, you can obviously check. And what I mean there is, if it was IPIs and the sensor is believed to be erroneous, you could remove that sensor string and take a manual set of readings. With some instruments as well, you can remove them from boreholes and check them. But with the majority, it would be looking really for what the causes could be in regard to what's surrounding what has occurred, and if that instrument, if it is possible to remove it and look at it if necessary. If it is just a known error in data, so a data entry point, it is possible to manually enter data onto the software systems and change that, and it does indeed keep an audit trail, so you can see that that has been corrected, so you can't falsify readings.
There is another question asking what was the ground mix used for fully grouted piezometer to serve as water standpipes. If I understand the question correctly, The fully grouted piezometers, like they are installed using a fully grouted method, and it's completely submerged into grout mix, and the water, the regular traditional in method of installation includes bentonite pack and a sand layer where the piezometer is installed. So those are two different methods basically. So they should be treated separately. The standard grout mixes are available in literature as well as in our website, in our method statements for regular applications. But again, usually for large application and delicate cases, we highly recommend to have a grout test program to find the best compatible grout for the piezometer applications.
Your question as well about in dam installations, is it possible to replace various instruments if they were to stop working? Largely that would be not if they are grouted into position. I have carried out some projects where piezometers are put into blocks on dams or in tubes where you use packers, so air inflated devices, and that was exactly that reason, so that those instruments, should they fail or should they need to be checked for some reason, could be taken out and replaced. Somebody else has mentioned, will the presentation be made available? We will actually have this available as a YouTube recording along with other Encardio presentations. So we'll make everybody aware of the location of that and make it available as soon as possible.
There's another question about like what is meant by DSL. That's, I think, on the TeraWeb, the deformation in millimeter and against a reference point within the structure. That's what it means on that particular, but it is highly configurable in our databases that you can derive the parameters out of the raw measurements relative to any particular reference point or reference measurement. So it's not a standard parameter. That's something that developed for the project, which is tied to a reference point on the structure, the deformation against that particular point. And there's a question about the software. And again, we in the Encardio group, we have our own softwares for our monitoring applications, and basically for geotechnical applications, we use our platform Drishti. For really TBM related and tunnel monitoring applications, we use our TeraWeb platform. You can find more information, and we can also send you more information about our softwares and their capabilities. Another question says, could you apply 6 meters of interval of an IPI to interpolate the data? I think 6 meters is on the high side, like we don't really recommend 6 meters. And we typically limit our maximum interval to 3 meters. And depending on the overall expected deformation. So 3 meters would be the maximum that can be, can produce reliable data. 6 meters is, I think, on the high side. Depending on the applications, the advantage of IPIs is that you can change the vertical interval based on the zone of interest. So at some zones, you can have higher resolution, shorter intervals, and you can increase that through the depth if you want, if the zone of influence is not you know, deep enough, or they can be adjusted. But typically, you know, we don't recommend going beyond 3 meters.
There's a question about, is there a system that can be installed outside of the dam body so that parameters inside the dam body can be monitored? That will depend on what parameters you want to monitor. If it's pressures inside the dam, again, it depends whether you have access to any of those locations. I'm just thinking of projects I've worked on where you can get inside and work in the gallery, or drill in stitch drill inside the dam from the gallery. I don't think it's exactly perhaps what you're looking for in regard to parameters, but we also have a system which is OPSIS, which is essentially you could set that up outside the dam. It will create a data cloud of survey points across the whole of the dam face, and by which you could also, if you have access inside in the gallery, you could use that same system to create a data cloud, and you can determine displacement of the structure with that system.
There's another question, and are we able to monitor both the pore pressure as well as the groundwater level using fully grouted method? Since the well is grouted, we cannot really call it the groundwater level anymore. So it's mostly on the pressure side, but the pressure can be extrapolated the overall depth of the groundwater. So like, we don't really monitor groundwater levels using fully grouted method, but we call, you know, usually that's the pore pressure in the wall, and can be interpreted for the depth of the groundwater at that particular location. So another question, have used your vibrating wire piezometer? It looks like sand cell in a canvas bag. Yes, that provides ease of installation, and that prevents any washouts of the sand, and makes you know, eliminates any air pockets around the piezometer. That's our method statement also describes how to install the piezometers within a canvas bag and sand. That's usual and customary, and we will be happy to support our customers during the installation stage, and to go into the details of that particular application. Another question, what is the common logging interval of IPI in states? 30 minutes per cycle. And there is no regular logging interval. Again, it depends on, especially for the TBM applications, when the TBM is close to the location, the intensity of the monitoring increased. I would say typical applications during the construction is around 15 minutes per cycle, which our system can easily handle. And so we monitor every 15 minutes and uploads the data accordingly within 30 minutes or in an hour to the database, but the monitoring is done usually in 15 minutes intervals.
We've run down most of them. If there are other questions, we will look through all of the questions, and if we see some that we have not answered, we will certainly come back to everybody individually. I think we've tried to keep track of those. The format in which they come in is quite congested. I think we've run through most of those.
Yes, I think I will check all those questions. If there are any ones that are not answered, we'll definitely send you guys an email as our answer. And you can see our contact information on the screen, and please feel free to reach us if you have any questions regarding this presentation or any other monitoring related projects.
Okay, so I think really just a thank you again to everybody who's attended. Thank you for taking the time to listen to our presentation, and stay safe in the current times, and we'll be in touch when we have another presentation to share with you.